Okay, guys, so I want to do a different type of problem for this chapter, but it's not from chapter 17, it's chapter 18. So we're not solving really this problem, we are just using the figure, okay? So here what I want us to find is to find the relation between the accelerations of pulley A, let's say, and pulley B. So let's say this will be A, and this would be here B. Let me put the camera. Here we go. So between A and B, so let's find, this will be pulley A, pulley B. So determine relations between, let's say, alpha A and alpha B. Okay, and here I forgot to put, I think the string here is going here to the middle, no? Is that correct? Yes. All right. And then the string's also going to the top. So this is exactly the type of problem that you see, you put here a force, and they ask you to find whatever, the tension of this force. Okay? So the next chapter is going to be the same thing we have done so far, plus you're going to have to add two equations, which is summation of forces equal to MA, summation of moments equal to alpha. But we are not doing that today. We'll just be doing half of the problem, which is the kinematic part. Okay? So let's say this will be pulley A, but let's start giving names now to points. So maybe that might become now a little issue since I use already A and B. So, all right, before we do that, in this figure, there is one instantaneous center. Can anyone tell me where it is located?
The bottom of point A.
Bottom of point A here. What is the definition of instantaneous center? Correct. So basically, you agree that this here, this rope here, is what's the velocity of this rope? 0, no? So it will look like this pulley is rolling about this cable, no? Or rope. Yeah? So really this point here is an instantaneous center. So what about, I know I always call them P, but this is at one instantaneous center. That's what I was asking. So the rope is here?
Yeah, that was the...
Okay, that's what I was asking before. And okay, so the rope, okay, so this one, so this one is located there, and this one goes to the center.
Yes.
And here there's nothing.
Yes.
Okay, thank you. That's what I didn't know. I should have checked that one. Okay, but question. I agree about this instantaneous center, everybody? What is this one here? Is it tangent or is it at the figure?
Tension's on the right side.
Yeah, I mean, this one will also be then an instantaneous center, no? So you want to call that one? Q or PQ? Okay. Now, but let's start now by looking at all this stuff. How you want to call the center of this pulley here? I know we use A and B. I should not use A and B, but
C.
C, the center. Then this point here, let's say, will be D. The center of this one will be E. Is that okay? Forget about the tension. I'll get this one here. We don't need it. So, in general, every time we need to find the relation. So, you agree that this could be a rigid body, this could be a rigid body, no? Which in this case are connected by a rope or a cable. What has been the procedure so far all the time is to start from a location that you know the velocity, and then to try to find the velocity of the acceleration of one point that is in common between the two of them. So, which point is common between both of them over here? E and D should be the same, no? Yeah? Okay. So maybe let's start from one point that we know. Let's try to find first the velocity. So we could say here what? So maybe we can find the velocity of C first from where? I mean, you could also almost go to point D directly. So we can find, we need to find this one, no? So let's go velocity of D. So what will be the velocity of D? Will be equal to the velocity of P plus omega of the pulley A cross S of D with respect to P. Okay? What would be VP? VP is 0, perfect. So here we have I, J, K. This will be a 0, 0, omega sub A. They don't give us any value for any of that stuff on the problem. Probably what they give you, at least should give you 1.
They give you the moment and the force.
Okay, it's fine. We are not solving this problem anyway, so. Okay, so we have this. Now, what will be the position of D with respect to P?
2 times the rate.
Yeah, let's just do symbolic since we have no values. 2R, 0, 0. So this will give over here, VD will be equal to what? 0 to R omega A. Perfect. This will be our equation 1. All right? Now, what can we do? We said we're going to compare E and D. Now, what can we do? We can find, correct, we can find VE, which we know should be equal to the velocity of D because it's they are located on the same rope, no? Yes, so rope will be moving at the same velocity. So this one will be what? VQ plus omega sub B cross S of E with respect to Q. What is VQ? 0. So what would you get over here? I, J, K, 0, 0. Omega sub B, and the position of E with respect to Q will be R0, 0. Perfect. If you want, we can make it even a little bit more general. The problem, let's say this would be R sub A, this would be R sub B. That way, we make it a bit more complicated. More general, okay, no more complicated. Is that okay? Okay. So basically now what do we get? Velocity of E equal velocity of D will be equal to 0 RB omega sub. And this will be equation 2. Right. What do we do next? Okay, so you see, you only need to equate the y component, no? So you can have 2, or this will be 2r sub A. You have 2r sub A. Omega sub A will be equal to r sub B. Omega sub B. Or if you want, you can, you can leave it as it is. But let's just write that, I don't know, omega sub A over omega sub B would be equal to RB over 2R sub A or something like that, okay? Or I think that might be easier. Let's say omega sub A will be equal to R sub B over 2R sub A omega sub B. I just write a different form because since we don't know what to solve for. But basically you see that the ratio of the other one would be equal, that the angular velocity will be equal to the ratio of some radius for the other one, no? Okay, here is pulleys, but something similar happens with gears, no? In cars and so on, no? What happens in a car when you increase the speed? The RPMs go down because probably the omega of the engine goes down, no? Does that make sense? Right, so related to that kind of stuff. Okay, so we did this for the velocities. So we found a relation between omega sub A and omega sub B. Now, we need to do the same. If we need to find out a relation for alpha A and alpha B, we can do exactly the same thing for the accelerations. Yep. Okay, so let's just do the same thing for the accelerations. That doesn't look like this class at all. I still need it. All right, so let's do the same thing for the acceleration. So first thing we can do is find the acceleration of point D. Oh, this is a good problem. So let's see, we find the acceleration of point D from where? Okay, good. So let's see. This would be a good review. So alpha, so A sub P plus alpha sub A plus S of D with respect to P. Do we have a relative term over here?
No.
Yes, no?
No.
No, we don't. Good. Okay, what should be the next line?
One or two.
All right, let's do them. Okay, that's fine. Let's do them. Okay, so it will be AP plus JK 0, 0 alpha A. What is the position of D with respect to P? 2R sub A 0, 0 minus omega sub A cross of. I'm going to write this a bit differently to give you a hint. It will cancel the whole Y component?
Just one.
Oh.
Just one radio.
It just cancels one, no? If you look at this is like if this was rolling from here to here, so you only cancel the component that goes from P to the center, no? Yeah? So remember, that's what I tell you. You need to go through the center, no? All right, so over here, do we all agree that then we can just cancel this one with what? One of these ones. Yes? If it's no, say it, okay? But all right. So then we're gonna get what? Acceleration of D will be equal to what? So will be 0 over here. A alpha A minus
Omega A squared.
omega, I forgot the square, correct? Omega A square R sub A. This will be our equation 3. Oh, I put 1, 2, so 3 this way. Because I'm using Greek numbers instead of Romans. Yes. That's what, you're probably absolutely right. I don't know what I was doing. Thank you. They still cancel because it's in the opposite direction. Yeah, you're absolutely correct. So yeah, thank you so much. And then that's what I was just thinking about. So you just cancel 1. Do I need to rewrite this on a different page or? No, it's okay? All right. So you cancel this one and this will be 0 over here, no? Only one cancel means here you're gonna have now omega sub A squared R sub A. I was just thinking about that, okay? That wasn't making sense. Yes.
So even though it's in the x component, we still cancel half of it because it's on the opposite end of.
Correct. I mean, I think it's easier you see. Jali, in this figure is in this direction, no? But when we started, we had kind of had it in this direction. So the component that was canceling was on the y, but in this case, since it's this way, it becomes on the x. Does that answer your question? I think that was what you were saying, but just want to double check. So sorry for that, okay? So we have this one here, omega squared R sub A. Now, what do we need to do? So be careful, we need to do now the same thing between Q and A. So now, what's going to happen? The whole component should cancel, no? Because we just go from Q to the center of this one. Yeah? So we can write now acceleration of Q, which would be the same thing as the acceleration of D, will be equal to A sub Q plus alpha B cross S of Q. No. Yes, S of. No, E with respect to Q. So what did I do here? Sorry, this is acceleration of E. Yeah, I don't know what I'm doing wrong today. It's acceleration of E equal acceleration of D equal acceleration of Q plus alpha B of E. No, of Q. Then what am I doing here? Of E with respect to Q. Not a good day, huh? Minus omega squared B S of E with respect to Q. And again, there is no relative term. So in this case, I mean, you can do it right away, but can we cancel this term with this term? Yes, no? Because this time, if you want, we go from here to here. And in this case, we're going from here to here. So let's see, ADP, no? Yeah, that's the difference, no? Between this one and the other one. So here we just go to here. So then will give us over here I, J, K, 0, 0, alpha B. Position of E with respect to Q, R sub B, 0, 0. So we get over here acceleration of E equal acceleration of D. Will be equal to what? 0. RB alpha B. So what do we do next? So let's equate, but I'm going to add one thing, y component of 3 and 4. Will give us what? 2R sub A alpha A equal to R sub B alpha B, or basically would be the same thing as before. We could rewrite over here alpha A equal to R sub B over 2R sub A alpha B. Okay, so basically you see that even we have a pulley connected, let's say whatever, by a chain, or if we have gears, we can still use the kinematics, no? To find the acceleration and so on. Okay, so really what's going to happen, let me ask you something because that will happen. Pulley A, what type of motion is pulley A having? Rotation? Okay, I agree. Does it have translation? Does that one move in translation or not?
Yes.
Yes. Yes, I mean, if it's rotating, it would be rotating about point C, correct? Is point C moving? Yeah, as you pull the rope, it will be moving up, no? So probably that pulley is moving in translation and rotation. What about pulley B? The same thing. The general motion of pulley B will be what? Translation and rotation, no? Yeah? Yes?
So, the velocities of
The velocities of what? Of the pulleys?
the translation.
No, because, good question. So for example, if you calculate the velocity, let's do it. If you calculate the velocity of C, it would be equal to what? Omega A, just talk about magnitude, would be omega sub A times R, no? Okay, but that's the one of the center. Now the one of this pulley is not the one of the center, would be the same. Oh yeah, it's the, yeah, in this case, it'd probably be the same because they are the one of, yeah. Or no, because I mean, no, because it might depend on the ratios of this one. So it will be half of it, no? Looks like. So the velocity of A, which is, sorry, the velocity of this one here, looks like will be twice the velocity of this one. Good question. Now, what would be the reason? Let me ask you, what is the definition of distance? Did somebody ask you what is distance?
The space between two objects.
Okay, velocity is distance divided by time, okay? So why one pulley needs to go twice as fast as the other one? Because it needs to cover twice the distance in the same amount of time. Is this what's happening over here? What happens if this moves one up? It moves one up on this side and one up on this side, no? Correct? So it moves two. But this one will be moving just one. So if this one wants to move at the same velocity of this one, then what needs to happen? This one needs to move the same distance. It wants to move at the same distance as this one. It needs to move twice as fast. Do you see what I'm saying here now? You agree that point A has to move 1 meter from this one plus 1 meter from this one, no? This one here only moves the 1 meter from one side. So both points needs to move at the same time, needs to move at the same, if you want, same ratio. So one needs to be twice as fast as the other one. I mean, think about which point would be going slower.
Well, so point C
Point C would be. Point C would be. No. Distance over time, so we'll be moving to yes. Yeah. Yeah. Okay, but you see, the equations can give you the results, but you can also look at it from the making sense, no? Distance divided by time. So talking about that, since just thinking about that, I don't know the answer, but we can look at it. It was one problem, I think, on the previous chapter that I look at it very quick. I said no, it would be too complicated, but just by looking at that, thinking about distances. Where was it? Let's see if we can find it. This one here, no? So determine the velocity of h. I just want you to tell me how many times bigger it would be. Just thinking about that. How many times the distance we'll have to do. So when this one is moving 1, how much distance will that one be moving? Okay, so take your guess, and now we're going to look at it. I took mine, 17,161. All right. Okay, so let's see if your estimate. To me, very good. We're putting the equation. I think it's 4. Okay, but let's find out.
Well, that goes the way
No, but just seeing how many times bigger it would be.
Yeah.
Okay, they don't. So it's only give us 120 and 40 already. What is the exponential degree here relative? Okay, so it looks like might be actually 3 on the ratio of these ones. So. Okay, so I mean, I thought it was the velocity. To me, it would be 4, but maybe we might have to do it, okay? They don't give us. So VH is 20, they found VH 40. And the original was 120, so it looks like it's 3 times. Oh, but we don't know the radius of this one.
Right.
Oh, so it's 120, 120, so they look from here. 1, 2, 3. Yeah, that makes sense. Yeah, I see what they've done. So basically, okay, what they've done over here is that this pulley here, okay, this pulley over here is fixed. Yeah. So really, what is this pulley doing? The only thing this pulley is doing is where the trick is only changing the direction. So if 120 the velocity is here, the velocity of this one would be 120, no? Yeah. And now we have 120 how many times? 1, 2, 3. All right? Yes? 1, 2, 3. So then we have this one velocity divided by 3, which should be then the 40.
So you have 2 lengths on the bottom point. 1 length.
Right, you get 1, 2, 3 lengths over here. This one, and this one. Okay? I mean, we could do it with a map, but let's just look at it this way. Does that make sense right here? Okay? Since we don't have that much time, somebody was asking me at the beginning of the class one problem, which I think is the assignment. What is the number of that problem you were looking at? What is it? Is it gone? Ah, right here. What was the problem number? 16135. 16135? Okay, let's go to 135. Okay, I don't want to look at the solution, but let's look maybe at the problem number here, 17135, and let's discuss it, okay? Because my experience is that if somebody has a question, multiple people have probably the same questions, okay? They simply do not ask it. So let me go back to 135. You see, this is something I'm going to do the next day, probably polar coordinates. Yeah, that's what I wanted to do. I'll do that next time. We are doing good on time, so all right. So maybe I'll go fast this way. 135. That one.
One was like, I'm sorry, that's an rounding error.
Okay. Oh, that was you?
Yeah.
The 0.0134 is what can I say? You know. All right. So this problem, let's see what we need to do. It's 134. No, 135. So the angular velocity of the screw. So basically, all this you could be just replace this by one bar, no? So omega alpha is C. No, omega EC is 1 radians per second clockwise, and its angular acceleration is 0. So that means basically that is constant. Sorry, that means that is 0. Yeah, it's constant velocity. Determine the rate of change at which the hydraulic actuator A and B is extended. So, all right, I'm not going to write down. So you're going to better write down the equations. So again, we're going to write down the equations and then you're going to solve it on your own, okay? But we're going to do the equations together. So like always, write down omega EC is negative 1 radians per second. Alpha EC is 0. All right? Now, what is the point that is in common between the scoop and this one? What is the point that is in common between this scoop and something else? D?
Well, D relates A.
Forget about D. D, what is the velocity of A?
0.
So is this on the same member as this one?
Yes.
So then what is the velocity of D? Then what is the velocity of E? Okay, so it's not D then. So which point could it be? 50% chance. B, I mean, we can do either one, but really personally I would say let's look at point B, no? Since we know here the velocity, no? Okay, so if we know this one is fixed, so what can you do now? Knowing this, you can find the velocity of C. What will be the velocity of C? The velocity of C will be VE. So VC equal to VE plus omega EC cross S of C with respect to E, which will be whatever. I'll probably do this in inches or instead of feet, or 1.5 feet, no? Whatever you want to use. So you find VC. You fully define VC. Now that you know VC, you can go and find VB. Yep. What would be VB? VB will be equal to VC plus omega VC cross S of B with respect to C. There is no relative term because the distance between C and B is the same. All right, next. We need to find the velocity from another point. We can find the velocity of B from where?
What?
A, okay? Because what we need to find is the relative acceleration or relative velocity. So is the distance between A and B fixed? No, so what does that mean? So you're gonna have the relative term. So you can write VB is equal to what? Velocity of A plus velocity of B with respect to A plus omega cross S of B with respect to A. What is VA?
0.
0. What will be the relative velocity of A with respect to B?
Yeah, no idea.
No idea. We don't know the magnitude, but we know the direction.
Yes.
So this will be the EAB. Yes?
Yes.
EAB will be this one along the bar. Okay, next, what can we do?
Also B and B.
We can equate the two equations.
So if you do that, you don't have enough equations and too many unknowns. So
What do you have to use point?
you have too many unknowns. If you go B, C, and B, A.
I mean, let me read the problem. I'm not saying, I'm just, then read it. So the angular velocity of the screw is 1 meters per second, clockwise, and the angular acceleration is 0. Determine the rate of change.
1/6.
Okay, yeah, I see what you're saying. Okay, yeah, so we did this stuff, and I think you are correct. So if we do that stuff, if we equate, well, it's good, if you want to do it, if we equate VB from point A and VB from point C, you're gonna have the unknown. Omega BC is gonna be one unknown. Omega EB is gonna be one unknown, but also the relative velocity of A with respect to B is going to be one unknown. So that gives you 3 unknowns for 2 equations. So that's not good, no? So maybe you were right at the beginning. So what do we need to do first, or at the same time? We can find the velocity of B from point D. If you find the velocity of B from point D, then you equate that equation from point D, the velocity of B from point D and the velocity of B from point C. You equate those 2 equations, and you're going to solve for omega BC and omega BD. Do all that make sense? I mean, if you don't write down the equation, it will be then difficult. So now that you have omega BC, VB is fully known. Yeah? So now you can equate the velocity of B from point A that had the 2 unknowns, the magnitude of the relative velocity of A with respect to B, and the omega AB. Yes? Yeah, I know you say yes, but then when you need to do it on your own, it's a different story, okay? But I mean, at least it's good. You understand. It's what I say. You understand, but then sometimes you do mistake because you don't practice. So now, yeah, this problem can be a little bit of a mess. I didn't notice that stuff. So we found the angular velocities and the relative velocity. So now we need to do exactly the same thing for the accelerations. All right, so, okay. So we first find the acceleration of point B from point C. Will it be any relative term? No. Then, now that we are smart, that we know what we did wrong the first time, next we can find the acceleration of point B from point D. Will it be any relative term? No. You can equate the 2 equations and solve for alpha BC and alpha, alpha BC and alpha BD. Yep. So now the acceleration of B will be fully known. Next, we find the acceleration of B from point A. So this will be the one with the relative term, no? So we have those 5 terms. So now those 5 terms, acceleration of A will be 0. Acceleration of A with respect to B, the magnitude will be unknown, but the direction will be the EAB will be along this member. Yeah?
Because it's close to accelerating straight out.
It is on a straight line, but this one is also rotating here, no?
Yes. So we want acceleration to be following, not the acceleration. Not the angular acceleration, but the vertical acceleration of the bar.
Okay, no, it's fine, yeah. So then that would be fine. So then you have the tangential acceleration, You have the normal acceleration, and then you have the Coriolis, no? Yeah, I mean, I think that's it, no?
That's awesome. Just the relative acceleration that we do.
Yeah, it looks like, yeah.
It's 1160.
Why did you have so many steps? Let's see what they are on the solution. Now you warn me here. So let's see what it is here.
Some shortcuts you can say.
No, let's see. It was 7137, no?
Yes.
135.
Yeah, for music.
I mean, it can be 2 pages, a lot of equations, but
Yeah. Oh, that's small. It's a small.
there we go. So let's see what I did over here. So basically, it looks like they, all right, acceleration of C. Okay, they find the acceleration of C, that's fine. All right, same thing, acceleration of B with respect to C. No relative term, everything is defined. They solve for, they should solve for omega BC and omega BD. I don't know what they do here. What the hell did they do to it? 7135. No, I don't want 134 is.
Is the answer to it is the answer to it is not.
All right, whatever. Did you understand the process that we just discussed? That's what I hate to go and look at the solution, tell the truth, I don't fully understand. This one I kind of follow. Here I kind of get lost when they start writing, okay?
From the solution project, question 17134.
17134?
Yeah, in the solution key, it's using the solution from 17.134.
Yeah. I think it's for the omegas, I guess, omega ED. I'm guessing. So you should also have the other omega, no? You need the omega BC, the omega DA, and then the relative velocity.
Yeah.
I don't know. I mean, that's what I'm saying, like, that's what you see that, Johnny, I never look at the solutions, no? I like to go through a process to find the solution. Basically, did you understand the discussion we had about how to find it? Did it make sense? Okay, so this part, the trick is that you need to take this step in order first to find the angular velocity of the bar BD and the angular acceleration of the bar BC, okay? All right.